Okay. Hello friends, today we are starting with the new new video on simulation of a physics computational problem for performance comparison between CPU and GPU. So for this we will be using CUDA, and this is a part of the video series that we are working on HPC and CUDA. So for performance comparison between CPU and GPU, I created a CPU simple simulation program that calculates the position of different particles with random velocities and positions under the effect of the gravity. So how does the program work? So firstly, it initializes multiple particles with random velocities and positions in a 2D space, and then calculates the position of the particles at certain time interval that is given by the user, and it repeats the calculation n number of times. So instead of putting print statements inside the program, which adds CPU overhead, I used the chrono high resolution clock, which will just give us the time for that was required for the computation to actually take place. So chrono is a C++ library, and it has a function called high resolution clock that can be used for this purpose. So before we start with the actual program, I must introduce you to some of the functions that were used in this program. So one is struct particle. So what this does, struct is a function that actually creates a data type, that is used to create a data type. So here we have created a data type called particle. So we are creating this data type so that we can keep similar types of data together. So x, y is the directions, horizontal and vertical positions of the particles, and vx and vy are the horizontal and vertical velocities. So next is initializing the particles. So for particle initialization, as you can see, p dot x, that's the position of the particle, we are just using a random function to generate some random value that will be stored as the particle x position, and this same is being done for y position. And similarly, we can also save the x and y velocities of the particles, and then we can move on to the actual simulation part. So this is the simulation function. So here we'll be calculating the velocities of the particles in the gravitational field, and then using those velocities we can calculate the actual positions of the particles with respect to their initial starting positions. So first we will update the velocity under the vertical velocity under the gravitation, because if the particle is moving upwards, then the velocity will decrease due to gravitation. So first we will calculate that, and then using these values of velocity we can calculate the values of the position of the particle using the formula particles dot I into Vx times dt. So particles dot I is actually the array that we are referencing for the particles. So as you can see, this is the complete code, and in the code I have given dt equals to 0.01. So that what that means is after every 0.01 seconds the calculation will be recalculated, and num steps actually tells us how many number of times this function needs to be repeated, and num particles is the number of particles that we are calculating the function for, and for now I have set it to 10 power 6, but we'll change it to get different outputs for comparisons. So as you can see here, it is auto start std chrono high resolution clock. So it will start the high resolution clock and show whatever the value it's at present into the variable called start, and then end. It will end the high resolution clock and store whatever value is in the end variable, and then we can calculate simply by end minus start. So whatever is being happened, that is the simulate particles function, that it will only give us the time taken to calculate this function. That's a much better approach than using a print statement and time command from the Linux terminal window. So as you can see, for 10,000 elements, 10,000 elements, we got an output of 0.97 seconds, and for 10 power 6 elements, we got an output of 98 seconds. So as you can see, there's a difference of 100 times, approximately 100 times. So now we get to the GPU code. So for GPU code, the code is essentially the same. The only difference is that a little bit of CUDA functions are added to make the code run on the GPUs. One of those is CUDA set device and the streams function. So as you can see, now instead of writing the particle initialization and simulate inside the main function, we have created two global functions so that these will be run on the GPU. Now inside the GPU, as you can see, we are referencing the particles using the GPU set ID. So what that CUDA set device is actually, what it will do, it will set a particular GPU for us to use. So it may be a GPU with ID 0 or 1, and accordingly we will distribute half of the work to each of the GPU for calculation. So here is the auto start command that we were using in the previous one too. But if you notice something, in the previous one we were just using it to calculate the time for particle, to simulate this particle, to simulate the particles. But here we are also accounting for the time it took for particle initialization. So that is something to note, because if we go to when we go to the outputs of the program, as you can see, they are very less compared to the CPU code. So what I mean to say here is, even after adding another function inside of this uh, time command, we are still seeing much better outputs from the GPU computing instead of the CPU computing. So it took 0.1 milliseconds to complete the program for 10,000 elements. Now if we go to 10 million elements, it will take 13 milliseconds. That's very less. If we go to comparing with the CPU performances, as you can see, for 10,000 elements it was 0.9 seconds, and as for the GPU it was 0.1 milliseconds. So it's 1,000-time difference between these two outputs. So this actually gives us a conclusive proof that GPU computing is much more powerful than the CPU computing, and efficient too. Thank you. That's it for the video. Okay, so now we can do a practical demonstration of the. We can now do a practical demonstration of the video. So as you can see, now we are inside this GPU node, RPGPU003, and now I can run the command module load SPAC. So SPAC is the administration software, management software, so which can be used to run unload different modules. So this is actually for environment setting. So we need to set up a SPAC environment before we start loading modules. So once this is done, we can load the CUDA module. Sorry, my mistake. It's SPAC load. And now we need to specify the exact version that we want to download, that we want to load. And now, yeah, the module is now loaded, and we can see we have the program here, simulation using CUDA. So I'll just compile the program. So it's giving us a little bit of warnings. That is because I was using a very large number for calculation, we can reduce the number while we are at it. Yeah, as you can see, I was using a very large number for testing purposes. We can reduce it to, let's say, a more realistic number. So 10 power 5, that's something realistic. Don't get me wrong, the 10 power, the earlier one that was 10 power 16 is also a pretty realistic number for CUDA computing for a GPU, but it would have taken more time, and since we just want to display give a this comparison between both of the programs, it's wiser to take something like this. So as you can see, 10 power 5 particles, and it took 0.84, so 84 milliseconds. Now if I were to do the same for the CPU code, so I'm sorry, CPU also I've done the same thing. Let's change it. So we can reduce the number of zeros to 5. That's 4. I can just add another. So that's we can, and now we can compile this program. Seeing simulation, we can check the output. So it's fairly evident that the CPU is taking much more time compared to the GPU. Yeah, 9.81 seconds. So it's a 1000 time difference between this and this. So with this, we can conclude the video. Thank you.